Good morning, everybody. I think we can get started. I hope everybody is doing great. So we're gonna finish off our tour de force through the different formalisms of modeling the gravitational waves from compact binaries. So we started out with PN, focusing on the in-spiral and the analytic machinery to obtain the analytic information as much as we can to solve the two-body problem. And then yesterday we moved on to pushing that approximation higher and eventually making it all the way to complete the in-spiral merger ring-down prescription of the waveform for compact binaries within the effective one-body framework. Now, one of the key elements yesterday, we looked at this without informing our EOB model with NENR, and we saw that looks really good. We push our analytic prescription higher through resummation techniques, and then we attach a ring down using black hole perturbation theory, and we get a very nice, smooth-looking in-spiral merger ring-down waveform that looks very, very good. But when we then compare it to full numerical relativity solutions to the two-body problem, we saw that they were not quite on top of each other. There was a relative dephasing, which is what you would expect, right? Because we have an analytic approach, we're going to resum it, we're going to include some non-perturbative information from the analytic side, but we haven't quite captured everything. And that makes perfect sense. And obviously, there has been a huge wealth of development over the last years. So one of your colleagues pointed out, if you go and look at the archive and at more recent papers, of course, right, uninformed, uncalibrated effective one-body models have dramatically improved over the years. The one I showed you was an extreme example from the early days to really make the point that NR information is really, really relevant. But obviously, the more analytic information is available from different strands, not just from PN, but also from Post-Minkowskian theory, and more recently also, from GSF, so gravitational self-force, the better the pure analytic prescription has become. But still, it's not perfect, so there's still informing through numerical relativity ongoing. And that brings us to numerical relativity. I've mentioned it a lot of times that we use this to make our models better. It's bread and butter, essentially, if you do waveform modeling these days. But what is it? I know that some people of you are working on and are in the audience, and you will have an entire lecture series next week on numerical relativity. So I'm not going to tell you about the details and how we actually perform simulations, how we reformulate the field equations in terms of an initial value problem, which obviously is the starting point for you. Thank you to the strong mathematical basis that there is, define initial data, and then actually perform the evolution. But I just want to tell you, obviously, we can do it. And it's necessary because all of these analytic approximation methods, right, asymptotically, eventually you're going to break down. And so in a strong field, we really desire to solve the full nonlinear problem. And the best method we have to do that today is to do this fully numerically, right, on large supercomputers. This has now been possible for about 20 years. The breakthroughs came in 2005. And there was a long build-up, right? You can go back in terms of looking at the mathematical foundations, like starting in the 1920s, until the big breakthrough came in 2005. And you can see here from Franz Pretorius' paper here, the extraction of the gravitational wave signal. There's also a plot of the motion of the horizons of the simulation in that very nice letter that you can look up if you haven't seen it. And you can see a very short waveform, but what you see is essentially the last cycle, the merger, and then the ring down. And you can also see at different times extracted here. So this was the starting point. Different techniques in the same year leading to comparable results were used by other groups, which was really good, right? So different methods, different types of initial data, different evolution schemes, and they all produced very comparable results. Now, as you would expect, right, this started off with equal mass non-spinning. So the entire system is entirely characterized by the mass ratio, which is 1 in that case here. And since then, of course, the big goal has been to include more and more physics into these simulations, produce longer simulations. And today, if you're not aware of it, there are thousands of numerical relativity simulations publicly available that you can access. Here's an example from the SXS collaboration, so you can go and check out the data there. There's other public catalogs from Georgia Tech, from the BAM collaboration, binary neutron star data. So, whatever your heart desire you can go and check it out. Now, I want to say a little bit about the parameter space coverage and why it's hard, and I'm hoping that the lectures next week are going to fill you in on all the technical details. But here are some examples of some of the numerical relativity simulations out there, and kind of where has the focus been, because that's going to be relevant for the question of, well, how good are our models and what sort of physics can they actually incorporate today? And so for the vast majority of time, the focus has been on simulating binary black hole systems that are on quasi-circular orbits, right? Kind of the approximation we have been making throughout as well, but we also saw in PN, everything is a bit easier to write down, still complicated, but easier. And the motivation has been, as I mentioned yesterday, that eccentricity is anticipated. You can show this in PN. And look at the leading order formula, is radiated very, very quickly. And so by the time you have very close separations, which is where our NR kicks in, we expect most of the systems, astrophysical systems, to be circularized. Now, that might not be the case depending on which particular systems you're looking at, but that's been the thinking for a long time. So if you don't have eccentricity, we have essentially a 7-dimensional parameter space that we're trying to cover. So we've got the mass ratio, and then we've got the 6 spin components. Yeah, so that's kind of where you are at, and the coverage is kind of limited in what we have, though there are thousands of simulations available. But think about it, a 7-dimensional parameter space, right? Even if you put just 4 simulations in each direction, right? That's a lot of simulations if you want to actually span that parameter space. So do keep that in mind. So today, most of the simulations are restricted in mass ratio space to being less than a mass ratio of 20. In terms of NR simulations, there are a handful of simulations at higher mass ratios, but high mass ratio is a real challenge. So do keep that in mind if you take your favorite Inspire merger ring-down waveform model and you evaluate it for a mass ratio of 100, right? It has maybe some GSF information that helps you tame behavior there, but I have no comparison data point that can tell you how accurate that model really is if you take numerical relativity as your gold standard. So just want to point that out. Spin magnitudes, the majority of simulations are restricted to 0.85 in dimensionless spin parameter. And that is mainly related to initial data construction. And it becomes more difficult, more challenging from a technical point of view. If you have a highly spinning curved black hole, you have a strongly deformed horizon, and that's going to make tracking this in your simulation much harder. Big focus has been on generally improving the accuracy of simulations because we're interested in the higher harmonics. You remember the decomposition of the radiation field into the HLMs. Now your dominant harmonic is your quadrupole, which is your 2-2 mode, but we're interested in higher order modes, mainly because they help us constrain parameters better. They help us break some degeneracies. And they're generally, obviously, very important also for signal-to-noise ratio in the recovery. So that's been, something that groups have been focusing on. And then we talked about this very briefly yesterday already, spin precession. So allowing for the spins to be arbitrarily oriented. And there was a question yesterday about the dynamics. Here's an example where you can see puncture tracks. So from one of the finite difference simulations in the puncture code, where you can see the relative separation vector of the 2 motions of the 2 black holes, and you can see this looks very cool, I think, but also very difficult if you want to describe that in some sort of analytic way, right? So that's the thing to keep in mind. Now, more recently, apart from obviously the mass ratio problem, longer simulations, people have started to think about eccentric orbits because there are astrophysical systems where this idea that eccentricity has been completely radiated away might not longer be the case. In particular, also if we maybe think about other detectors with higher sensitivity at low frequencies, etc. And then we can go to the very extreme case and not have a closed form eccentric orbit, but a hyperbolic encounter, or people also refer to this as a scattering process. So where we don't actually trap the 2 black holes, but they're coming in, like think about it in the classical way when you have a scattering problem, right? You're shooting 2 particles at each other. In our case, it's 2 black holes. There's a specific impact parameter, and they just get flung out and scatter away. And so, there might be a case for those too, But what's particularly interesting about this, for those of you interested, there has been recent theoretical work showing that you can map these scattering problems onto the bound problem and help improve the analytic side. So that's why it's also quite exciting, because remember, we want to push our analytic information to better and better order. So this is just to give you a flavor and an overview of the sort of simulation space coverage we have available today. Now, clearly this is a lot, very exciting. So why bother with analytic stuff? Why not do NR everywhere? Right, and be done with it. If that's the best you can do, just use it and don't bother with anything else. There's probably a long laundry list that one could put up here. I've put on a few things. First of all, it's computationally expensive, right? Each of those simulations is hundreds of thousands of CPU hours, depending on the accuracy, depending on how complicated the system is that you're simulating, depending on the type of code you're using. So that's already bad, especially if you don't want to kill all the trees. Dimensionality I mentioned before is difficult. Where do you put your things? And if you think about the sampling problem, right? If I have my prior and I draw points from my prior, well, who guarantees me that I have done that simulation, right? So I want some sort of continuous coverage, and that's what the semi-analytic waveform models are going to provide us with. If you don't want to do any PN or UB, then you really want long simulations, right? I want to be able to take one of your favorite low mass-ish observations to date, which has in-spiral merger ring down in the gravitational wave observation band, but is not dominated by the merger ring down that comes at high frequencies, but has a long in-spiral in it, right? So anything from a BNS, a low mass NSPH, even low mass BBHs, right, will be that. Your standard NR waveforms that we have today in the typical length, which is kind of indicated in red here, you will not be able to cover that for those masses. So, you know, we have had quite a few observations in that region, so that's certainly not sufficient. Unless you are capable of actually simulating these in numerical relativity for a very, very long time. So here you can see the longest simulation that's been carried out to date, as far as I know, which is a mass ratio 7 and has 175 orbits and was produced by the SXS collaboration. But that's like one data point, right? Just to give you an idea. High spins are difficult because of initial data constraints predominantly that we have. So you can see examples here with different types of initial data. One can push it higher than this 0.85 roughly-ish, where most of ours are concentrated. But for example, Bohn-York initial data, which are a particular type of initial data that are being used for binary black hole spacetimes, have a fundamental limit of 0.93. So if you want to simulate anything beyond that, you have to think about the kind of initial data that you actually use. So this is just an example here under the unequal masses. That's the other question, right? So y is kind of 20-ish up to where we go. So if you have very, very high mass ratios, right? So you have a very small horizon and a rather large horizon, but you are discretizing your evolution equations, right? So both your time stepping and essentially the resolution, the spatial resolution required, are going to be set by the size of the smaller black hole. So that's just going to make it even more expensive and complicated. So that's why there is, you know, people are working hard on overcoming these technical limitations, thinking about different techniques, how one can evolve. But this is just where we are at the moment. So if folks are interested, there's lots for you to do in the future. Yeah.
Do you know any chance like where the conditions face initial conditions of this thing? Why is there
comes from some of the fundamental assumptions that go into the construction of the Bohn-York initial data that you can overcome in parts by using different kinds. So here, for example, the superposed Kerr-Schild initial data that allow you to go beyond that. But there is a fundamental limit in the Bohn-York data based on the assumptions that go into the decomposition itself. But we do have thousands of NR simulations available. And we can use them in parts of parameter space, and we want to use them as data analysts. And we use tools in order to make that happen, because you want to continuously sample your prior, but you have a sparse, discrete set of numerical relativity simulations. So how can I marry these two together? And for the past, 10, 15 years has been very nice idea being brought forward, which is called reduced order modeling, which allows us to take something that is computationally expensive and slow and discretized and turn it into, in a smart way, into essentially a continuous coverage that we can use for parameter estimation, for example, if that's what you desire to do. So here's a very nice illustration of the very basics of how this works. So can we have a pure NR waveform model, even though we only have a set of simulations? And the answer is yes. And the algorithm or the kind of framework that's being proposed here is what's called reduced order modeling or surrogate modeling. People often use that interchangeably. And it's a way of compressing information. You can think about it also as dimensional reduction. So I start with a discrete set. I do some smart manipulations. And then at the end of the day, what I do is I'm going to interpolate between my discrete set in order to essentially fill in the gaps and have a continuous waveform manifold, which then allows you to evaluate that model at the parameters that you desire within the space that you have built your model over. So let's look at this in a sort of illustration of how this goes. And this is literally an algorithm you can implement yourself and work through. And it doesn't have to be a numerical relativity data set, right? Think about it generically. So we started out with a discrete set in an R. We have time domain waveforms, right? It's a time domain solver, so we get nice wiggles back. But we only have M of them. And each of those waveforms is discretized in time, so it's a time series. And it has some parameters, some physical parameters, right? So in our case, mass ratio and 2 spin vectors, so seven dimensions here. If you look at this kind of very nice diagram from Jonathan's paper, so this is kind of the time axis, and this symbolizes here different sets of parameters. And each of those, we have some M lines here that would be sitting in here. That gives us our initial data set. With that we start, so our training space, if you want to use modern lingo for that. Now, the first thing I recognize is I don't actually need all of these waveforms to represent the space that they span. And I'm already choosing this language on purpose, but I can actually find a subset of waveforms that can act as a basis that I can use to decompose that discrete set and then reconstruct the original waveforms and everything in between from it. And that's what we call the reduced basis. So that means I pick certain parameters, lambdas. So that's your compression in parameter space. So dimensional reduction in that sense, yeah? If you do that, then you think vector space, and I can then reproduce my original input waveforms roughly as these basis vectors now, times some basis coefficients summing over, just like you would do in a normal vector space, right? You take your vector A, you have some, let's say, Cartesian coordinate system, right? Ex, Ey, Ex, and I've got some components in front of it. The sum over that will give me my A vector. Think about it really analogously in that space. Now, the question is, how many basis vectors do we actually need? So what's enough? And how can I get to them, right? How can I distill them? And so, there's a twiddle here, because the question is, how large of an approximation error do you want to make? And that's your choice, and that should be driven by your application at the end of the day. And so a common tool to use is essentially something like, an L2 norm error here, where we have our true waveform that came from our training space, which subtract its approximation in the reduced order basis space. And we find that it has some error against all of them in my set. And I want this to be, less than some tolerance that I have chosen, right? That's a choice you have to make. You have to decide what you think is good enough for the problem you are trying to tackle. So once you have that, that will give you then a set of n basis vectors. So out of my discrete space with m waveforms, I have now chosen n of them. And of course, if you're doing a good job, then this n should be smaller than your m that you started with, right? And that's kind of indicated here. The red lines here in this kind of picture are now your n basis vectors that you have distilled. So that's great. So that's compression in terms of parameter space, but they're time series, right? Each of those waveforms, when you sample them, has like many, many data points. Do we need all of those data points? And the answer is, no, you don't. Okay. And my laptop no longer responds. Very good. So we can also compress in the time dimension, which is very convenient. So it turns out that not all times are equal. Some times are more important than others. And if you think about the phenomenology of a gravitational wave, that's probably not too surprising, right? So I don't know if this works, but I'm going to try. And so, is this big enough? Kind of? Okay, right. So if we have this and this wiggle in the time domain, right? We have some sort of small growing thing, and then it goes big, and then it goes down again, right? So if you think about this, oh, including memory because of my poor drawing. If you think about this now, in terms of, you know, I want to represent this wiggle to some high degree, you probably, if you go further back, right, this is just gonna go like, go down this way. So I guess intuitively, you'd probably already say, well, I probably don't need so many time samples out here, right? Don't need to have like, I don't know, at a cadence of 0.1 m or something like that. But as I go and change the morphology of my signal towards the merger, that's probably when you want to have a little bit more representation. And that's generally what you do find, right? So the time compression algorithm allows you to select now the most important data points, and they will normally correspond to the ones where you can see a strong change in the morphology of the signal. And so how do you do that? By something called an empirical interpolation algorithm to determine these nodes. So they are here denoted as TJ. So in our graphical picture, these are the blue dots. So I no longer need all this continuous or, you know, very, very densely sampled time series, but I'm only going to select out a few T's out of those. And you can also see they're not equally spaced, right? So they really take into account the shape of whatever the underlying function is that you're trying to compress. And so that's the formal expression of this, where we have our reduced basis vectors here, and then here our n components, our n time components. And so with that, we can now in principle reconstruct our original training space set to a high degree of freedom, of course, limited by the error threshold that we essentially set initially. But that's not all we want, right? This is great if I can reproduce what I originally had, but I want more. Yeah. Yeah, so the n is the number of the selected basis vectors that you have, smaller than m, if you did a good job.
Then the error is set by the, you spoke about tolerance and you want to lambda. The lambda vector.
No, so the tolerance is on the reconstruction. How well do you reconstruct the function you started with if you decompose it in a, you know, in a set of basis vectors that is smaller than all the waveforms you had before? That's your error, right? Yeah. So this is your difference here. How good is your, it's an approximation error. Yeah? Okay. That makes sense? Cool. There was another hand up?
So I have my waveform, say, just in the subspace of the parameter space.
Mm-hmm.
This model gives me the other waveforms, interpolate subspace, right? Not all.
Yeah, that's right. That's right. So we're coming to the next thing here, which is now our parameter space fits, right? Because at this point now we have a sparse representation in both the time and the parameter space axis of our original training set. But that's no good, right? That's still, I mean, that's good, but that's not what we want. That's not the ultimate goal because we want this continuous coverage, right? So what I need to do is I need to fill in the gaps, right? I need to fill in a way, find a way to be able to predict what the waveform is going to look like at any lambda that was not in my original training space. That's what you ultimately want to do, right? You want to predict what the waveform is going to look like at a point that I haven't been able to simulate with NR, or I just didn't have an NR simulation to start with, yeah? And so we need to fit. And so these global fits are the really tricky bit now, because I don't know how familiar you are with fitting routines in high dimensions, but that is mathematically a very challenging problem. Yeah, so that's why one of the goals is to find, good interpolations, good parameter fits, but also to try to break your problem down into smaller pieces, because that will normally help you to have more robust fits across your parameter space. And once you have that, then it's really nice because I can now predict the waveform at an arbitrary lambda prime based on the simple decompositions and compressions I had done before. Now, because this last bit is really tricky, there's different algorithms out there, different approaches that people have been using to do that. But the thing you should always keep in mind, make your life as simple as possible. Think about anything that has very, very complicated morphology. Well, that's not very complicated, but it could be significantly more complicated. You might not, if this is your H plus, this might not be the ideal function to fit. So think about whether it makes more sense to decompose that problem into something that looks a bit smoother. So people started out, for example, with imaginary and real parts, but then amplitude and phases have a much smoother behavior and make your fitting easier, for example. Yeah.
Going back to the does the node stay the same across?
Yeah. Yeah. So the nodes are the selected ones from the empirical interpolation algorithm. That's a fixed set for all of it. Yeah, absolutely. So you have essentially, and this, of course, you can think also this works well when you know you have a parameter space that's kind of smoothly varying, right? Where you don't expect some crazy changes, because then, maybe your selection wasn't optimal for that and you're not actually well representing that data point. But for, so far we haven't had any indication, at least in the parameter space, for most of it that we would anticipate some discontinuous behavior, right? That's essentially the thing. Now, current state of the art, if you want to look at surrogate models, is NSR70Q4, which is models, I don't know if you focus on it in the audience, which was built based on about 1,500 numerical relativity simulations. You can see the distributions of the parameters here, so you can see the spin magnitudes, and then so here in the spherical decomposition, the azimuthal and the tilt angles relative to the orbital angular momentum, as well as the mass ratio. I don't know how good your eyes are, but this goes here up to mass ratio 4. So that already tells you kind of the sparse limitations in terms of the parameter space. And the spins, obviously, here you can see go up to 0.8. So again, right, if you want to extrapolate and you're interested in very extremal scenarios, you have to think about whether your model is still accurate enough or not. And in terms of length and our simulations, I mentioned, right, we simulate from a certain starting separation, which means we have a given length. So NSR70Q4 you can use for binary black holes that have about 60 solar masses in total mass, and that will allow you to generate a waveform starting at 20 Hertz. Right? If you want to generate your waveform from 10 Hertz, you have to go to significantly higher total mass. Right? The whole waveform scales with the total mass. I've said that before. For BBH spacetimes, it's just a rescaling. But so that's why it is not applicable to everything, right? So if you remember the stellar mass plot we had in the very first slide, there's quite a lot of observations we have that are below that mass threshold. So there, we would not be able to just analyze the data with the surrogate model. Yep, that's the question at the back.
So the NR ones, they like is the parameter space, right? So presumably they're more biased, not spinning equal mass.
Yep.
So does that affect like the surrogate models?
Yeah, I mean, they're absolutely right. So you can see at the end of the day, this is still sparse, right? As we said before, right? 7 dimensions, 1,500 simulations is not that large. You're absolutely right. So what goes in there, and if you look at the distribution in the catalogs, now there's been a recent release, so there's a lot more simulations, and I believe recalibration is ongoing at the moment to incorporate more and expand the parameter space. But you're absolutely right? If you look at the density, you'll find a lot more simulations that are nearly equal mass, that are aligned spin, anti-aligned spin, or some combination. Equal spin space has been explored reasonably well, also with different codes, which means we can have good comparisons on the error in the NR itself. But yeah, you're absolutely right? It's a layered problem where certain subspaces will have a much more significant sampling than others.
So like
sorry, say again.
Do they do anything to kind of counter that effect so that they're not biased towards like the catalog ones, or is it?
You mean some independent testing?
Oh, no, they make their modeling so that they're not biased towards the people mass and non-spinning pieces at the expense of maybe higher mass ratios.
I mean, they're all treated equally, right? But the truth is also, if you do then a fitting routine, right, fits will normally be less well constrained in regions where you have less data points to actually constrain the fit, right? So, but overall, the accuracy of NSR70Q4 in the parameter space that it was calibrated over is pretty good. I'll show you a result in a couple of slides. There were more hands up. There was one in the back.
Is it possible to just like construct a basis band to serve instead of using waveform?
So GST-LAL, which is one of the search pipelines, they use SVD algorithms, which has kind of the same sort of idea, right? That you decompose the bank into the dominant directions, if you want that way. Now, the metric that was introduced yesterday, for example, the T0, tau0, tau3 metric in the BNS space is also, you can think about it as something where you have predefined where the most variation is going to be across your parameter space. And that's kind of analogous, right, to a compression, because you're capturing where the largest directions are. So I'm not aware of, I don't know, are you aware of any reduced basis direct use in searches? Yeah, near SVD. Yeah, that's right. But beyond that, I'm not aware.
In your language, in the previous slide, maybe the geometric template values also some kind of reduced basis.
Yeah, that's right. Those are the two I mentioned. Yeah, but okay. Not sure I've forgotten anything, but those would be the two that come into mind, which are kind of similar-ish to the in terms of the base idea. So I did mention this is the current state of the art, but there are lots of other surrogate models out there. When I say current state of the art, I really do mean this is what we currently use in the actively ongoing analyses of the data of the current observing run. But there are lots of other surrogate models out there, and they don't necessarily only have to be numerical relativity surrogates. You can apply this methodology generically to anything that is slow. And I'm going to point out that, of course, EOB, we said, we love to use it, but we have to integrate lots of ODEs, right? That makes it computationally expensive. So you can think about it as it also being a slow model. And there's lots of literature out there over the years where people have produced surrogate models or reduced order models of EOB waveforms in order to circumvent your ODE integration, right? So you have the offline cost where you need to generate your training space in the first place, just like you do with numerical relativity simulation. But then you can speed up the problem later on. And that's something we have used significantly in previous observing runs, for example. Now, here's an example for NSR7D-Q4 for a generically processing system here at some particular orientation in the sky. And you can see in orange the reconstruction from the surrogate, and in black you can see one of the NR waveforms that were used in the calibration here. And it has a very, very good representation. That's just to visualize it. Now we want to make this a bit more formal, and that's now the opportunity to actually write down the formula for the match or the mismatch, which you've heard of before. And you've seen this formula in a slightly different way yesterday already. But what we define is a noise-weighted inner product, sometimes denoted with angle brackets, sometimes with round brackets, which is just given as 4 times the real part. And then we integrate between 2 frequencies we're interested in. And we have waveform 1 times waveform 2, complex conjugate of it, normalized by the power spectral density. So meaning if you have a different PSD, right, this agreement or disagreement, so this kind of inner product will be different. And if you have no noise, of course, then you get the full intrinsic irrespective of detector type of agreement. Now, what's the match? Or if you look in the literature, also sometimes referred to as the faithfulness. So kind of think really about it. How well does one waveform agree with the other waveform? So this is obviously normalized here. And we also maximize over the nuisance parameters, which are our reference time and reference phase. And that gives us something that is 1 if they're in perfect agreement, and 0 if they're kind of totally orthogonal to each other, right? Really think about it like how you would compute a distance in a metric space. And so what's most commonly used is the mismatch, which is just 1 minus the match. So just to have the lingo in your head. If we have a more general space, we'll also need to do a little bit more on the numerical optimization, but just for those of you interested. But generally, that's all we do. Normalize your waveforms, compute the noise weighted in a product, and maximize over a couple of nuisance parameters. And that will tell you how well two waveforms agree with each other. Now, if I build a model of something, then of course I want to know how well does my model agree with the original things I had. And so here you can see the mismatch distributions for the NR surrogate, specifically here. So look at the colored lines here. So these are the mismatches of the surrogate now to the different NR simulations that were being used. And you can see it's a nicely Gaussian distribution that's peaking around a few times 10 to the minus 4. So that's roughly, to give you an idea, that's the sort of accuracy level we are at. Now, the question is this worse than an R itself or not? And that's what the black line is going to show you here. So this is essentially a mismatch that shows you the NR error itself. So you run your simulations at different resolutions, for example, right? That will give you a slightly different numerical result. And then you want to know, okay, if those are my two baselines, what's the difference between them? And you quantify that again in terms of the mismatch, and you'll find the black distribution here. So the takeaway message here is, on average, right, the NR surrogate isn't going to make it any worse than the intrinsic NR error already is there, which is good, which is what you want, right? If this was significantly off to the right here, that would be very bad. So the NR surrogate, at least in the space it was trained over, right, plus the points in between, is doing an excellent job, is a very, very accurate model. Yeah.
So now I'm bored. So there's like a phase transition. So the effects that you can measure are effects that make a mismatch of larger than a percent roughly.
Mm-hmm.
You can understand it from the fact that the SNR square of the event is kind of like 100, 400 for the period. Now, the 10 to the minus 1 there,
Mm-hmm.
this is totally measurable. So if you have mistakes in the NR that are 10%, then the inference is going to go completely wrong. And so what is this cornering parameter space and how can I avoid it?
I don't exactly know which part this one here is, but I assume this will be orientation average. So I assume you'll have probably things here that are challenging, right? High spins, high mass ratios, large inclinations. Things where high order modes will become important, right? Where we know that the resolutions in the simulations might not be where we would like it to be in order to increase the accuracy.
The entirety of higher modes is not 10 to the minus 1, right?
The entire 10 to the minus 1.
The entire effect of higher order modes is not reaching 10 to the minus 1.
Well, as I said, right, this is orientation average probably. So you take in, so this depends very much on, right? If you see edge on, you're predominantly not going to see the 2-2 mode in your recovery. You'll predominantly see the higher order modes, especially the 2-1 will be quite dominant. And the 2-1 is one of the trickiest modes to model. So as I said, I don't have the exact map here, but we know from comparisons that the models do very poorly generally when you go to the extremes of the parameter space. Right? If things are moderately precessing, they're fine, moderately asymmetric in mass ratio, they are okay. But as soon as you start pushing, we do start to see differences, and we also do start to see problems in the NR simulations. Yeah. But yeah, you should be worried. I am worried too. And here's just another example that you can do this. Here's an example for the EOB side of things that I mentioned before. So a slow model that we have surrogated here in this case. And I wanted to highlight this as an example, because this is one where we used machine learning. So if you have been pondering about these complicated parameter space fits and high dimensional splines are very difficult, for example, you could use things like Gaussian regression algorithms, which is what the surrogate uses. And here we use the neural network. to help us out. So if you are somebody who's looking for using AI in waveform modeling, that is something where it's definitely already being used. So just as a side note. All right, that was all I had to say about NR surrogates. So I'll give you an idea of how it's constructed and what the current state of the art is. Are there any last questions on that? Because if not, then we can move on to the final waveform family, which are the Phenom models, which also have undergone, lots of revolutions. So what's the idea here and what does phenomenological mean? So the original motivation here is that everything I've told you so far was in the time domain, right? We have looked at time domain waveforms throughout the entirety. But you heard yesterday already that most of our data analysis naturally is done in the frequency domain because the variation of the noise in the detector is characterized by different frequencies. So this is the natural way where we do our parameter estimation, our searches. But that means you have to do an FFT. FFTs are expensive, and especially you can't use the stationary phase approximation, which would help you everywhere in parameter space. So FFTs really is a large cost, computational cost in the whole pipeline. And so the original motivation was, well, let's circumvent this and build frequency domain models that capture, inspire, merge, or ring down straight away. So let's not bother with time domain. Let's go straight into the frequency domain and do that. And here's a nice example of why you do care about this. And you can see evaluation time of a waveform model all on the same core. So we use the same hardware, so we can actually compare that as a function of the mass of the binary for an equal mass binary. And SUB in our V5PHM, so the latest flavor of the effective one-body family that includes precession and high order mode. If we take like a 150914-like binary, right, 60 solar masses, you can see this is on like 0.3 seconds for a single waveform. Now you want to do Bayesian inference. 10 to the 6 to 10 to the 8 likelihood evaluations. Every likelihood evaluation, you have to generate a waveform. You can do the maths, right? So if people shout at us for, why don't you give me these results in 2 hours? That's part of the story, I would say. And you can see a bunch of other time domain waveforms here as well. And you can see the range is quite large. So what we're interested in, right, is pushing this curve down. Ideally, the sort of millisecond range. This is kind of where we want to go in terms of individual evaluation. But you don't want to trade accuracy, right? You still want to maintain your accuracy because otherwise you get what Barack was saying, biased inference. So Phenom models essentially try to use all the analytic information that includes EOB, for example, and NR and combine it together and give you a fast waveform model that is still accurate. So that's kind of the basic goal. And I'm going to walk you through an explicit example for the latest generation of, well, one of the latest generations of Phenom models here in the aligned spin sector. So this is IMR Phenom X, my current generation X, AS for aligned spin. And as I said before, with all of these sort of techniques where you're kind of trying to fit some sort of manifold, you want to make sure you start with a smooth data set, right? Something that makes it easy for you to kind of build some closed form expression that encapsulates the physics. And so now we have moved to doing this mode by mode. So we decompose our frequency domain mode, HLM, theta the parameters here, into an amplitude and the phase for each of those modes. And you can see examples here. You can see the amplitude of one of the 2-2 mode here is a function of frequency. And we have seen this picture before. This looks very simple, right? Very smooth. So people drew it on the board. I had a plot of it, but you see the nice kind of decay. Then we have the merger phase. And then we have the ring down, which on a log-log plot is just a straight line. That's quite simple. For the phase, we have moved to not looking at the phase directly, which is just a growing function rate, but at the phase derivative, because it reveals a very nice structure that we can use to our advantage in order to actually model the waveform. And so this feature here is the onset of your ring down of the dominant quasi-normal mode in the ring down. So the 2-2-0 in the case of a L equals M equals 2. Now, what we do, you can see colors here. So what do these colors mean? We split it into different regions. So we have kind of this in-spiral region. Then we have an intermediate region, that's the green region here. And then we have this merger ring down part here. And we do that both, the phase derivative here and for the amplitude. Now, how you define these boundaries, that will differ between different waveform models, but it's always kind of inspired somewhat by physical intuition and by concept. So in particular here, the first bar you can see here corresponds to the frequency of the minimum energy circular orbit. And the green part here to the innermost stable circular orbit. Remember, this was the point where we traditionally would say we no longer trust analytical evolutions, so to say. And as I mentioned before, this dip here corresponds to the ring down frequency. So once you have done your split, you go back and take all the information you already have, and you already have a lot of information, every single one of you, right? Because we know already, we have PN that gives us a pretty good prescription of the early in-spiral. For example, we're in the frequency domain, so why not take our closed form Taylor F2 that we have talked about the other day? So we start with this, but then obviously we realize, right, we are here. We're not just in an in-spiral. We are kind of transitioning into the strong field regime, and we know our PN isn't good enough. So let's artificially extend it. PN is a Taylor expansion, so let's add in some pseudo-PN terms to make that series go a bit further. And that's exactly what you see here, right? And so in this particular case, there are 4 coefficients, and it's a polynomial. And if you write down Taylor F2, and then you see how we're going to continue the counting literally in the standard form. So we have F, then 4/3, 5/3, F squared, 3/5 F squared, and so on and so forth. So we'll just continue the counting. But eventually, this is not going to be good enough anymore. So we see the shape of change, right? The change of shape here. And so we need to transition. So we pick another ansatz, and we smoothly join these together. And this is not really inspired by any sort of deep insights, but something that works. And so traditionally today, people use just another continuation of a polynomial ansatz, and then connecting to the transition for the ring down using essentially a Lorentzian in the frequency domain, because that's the shape that you experience, right? And so the ring down itself then is exactly modeled by that, because that's what we analytically know from perturbation theory, right? So in the very early in-spiral, we have what we have from PN, and we continue it. In the intermediate region, we are a bit creative. And in the ring down, we again draw on analytic information we already know from perturbation theory. And you join these 3 stages smoothly together, right? And you do the same, obviously, also for the amplitude with an appropriate ansatz, not just for the phase. So we have a bunch of coefficients, right? So here we've got 5, here we've got 1, 2, 3, 4, 5 coefficients here, and then we've got another bunch of coefficients down here. And these are what we call the phenomenological coefficients. So kind of eventually need to fit them. Now, to do all of this, I need one key ingredient, and that means I need a data set again, right? I need some sort of training space over which I perform my information now of these phenomenological coefficients. And so what we need to create are what's called hybrid waveforms. So we take our best analytical that we have, which could be your latest EUB, for example, and we hybridize it up to some evolution, right? MECO, for example, or the innermost stable circular orbit. And then we join it smoothly together with numerical relativity simulation. And so you can see an example here where we have in red, you can see an in-spiral waveform. And then in green, you can see a numerical relativity waveform. And in this dashed overline, you can see what happens when I join these 2 smoothly together over a particular window that I have chosen. And there are subtleties in that, of course, how you actually construct your hybrid. But that's a key ingredient and one of the things you really, really need. And so schematically, really, you can just say, right, my phase and my amplitude will then just be what I have from PN in that case, or it could be EUB, and from NR, right? And then smoothly joined with transition functions, linear transition functions normally in this window here. And once I have my catalog of hybrid waveforms, I can now actually go and construct these phenomenological coefficients, right? I need to know what they are given a set of parameters. And in the different approaches, again, you can do that. Direct fits used to be what was kind of standard at the beginning. Works quite well if you have a low dimensional parameter space, but if you increase the dimensions, it becomes more difficult. And so in the past couple of years, hierarchical fitting methods, where we split essentially the problem, layering it, similar to what your colleague asked earlier in terms of the complexity of the physics, and also not fitting, across the entire waveforms, but being smart about it and using collocation point methods, which you kind of can think of akin to selecting particular nodes in your time series that are going to be quite important. And if I know the value at that particular node, I can actually reconstruct it across the entire domain. And so that's exactly what people are doing. So people split it into the different physics layers, right? You start out with your non-spinning data. They're entirely characterized by your mass ratio, nothing else there. Then I can say, take the other data set now, which are my equal mass, equal spin data. That's a particular direction in parameter space. Have your fit there, which incorporates now your spin dependence. You combine them together hierarchically into a higher dimensional fit. And you continue until you have your full, in this case, three-dimensional fit, because this was the aligned spin example, right? So the non-precessing ones have got the mass ratio. And then there are different ways of how you could parameterize the spins. And so what's found to work quite well is here essentially an effective spin and then a spin asymmetry that tells me about if I have unequal spin. So that has been found to work quite well. Here's the final example for one of the comparisons in the Phenom XAS paper for the phase here, or the phase derivative. So in green, you can see the collocation points. Now, it probably doesn't look too surprising, right? So this is here in the ring down phase. Well, obviously, there's a collocation point right at this frequency, because that's clearly morphologically an important point. And we also want to capture the turnover. You can choose different methods for choosing collocation points. Chebyshev, Gauss polynomials are a common tool that is being used. In black underneath, I don't know if you can see it, you can see the original hybrid data that were used. And in blue, you can now actually see when you evaluate our fit here and the answers on the previous page, and we get residuals that are, they are very, very small. They are not perfect, but they are very small. Now, if this sounded all very alien, oh, sorry, there's a question.
I'm trying to understand. So in the dimensional expansion or expansion parameter is velocity. And then you show how you can add more terms. You use that like a polynomial as well. Is this the velocity or parameter expansion as well?
It's related to the frequency of the wave, right? So you can write your velocity parameter. This is just pi mf to the 1/3 in post-Newtonian theory, right? Pi mf, f is your gravitational wave frequency. And we are modeling this here in the frequency domain, right? So that's why you can just continue it with the appropriate powers as a function of f, and we scale the m out because everything rescales by m.
So I'm trying to understand. So you say like, okay, I will have some expansion parameter that is similar to the Pn, and I will have some coefficients and components, and you just keep it.
Yeah. Yeah, that's in a nutshell, that's it. Yeah. Practically, here's an example that I thought might be useful, because at least in my head, when I look in the previous two slides, I'm like, I'm not quite sure how I go from a complicated fit to actually evaluating a waveform model, right? And so let's make a simple ansatz. We have some function, right? So this is akin to our complicated Phenom ansatz that we've chosen, right? But this is a simple formula, it's just a quadratic polynomial here. We choose now particular points. So this is just a function f as a function of x, right? They're not mapped to each other. I just stole those from an old paper just to illustrate the point here, right? So we first want to determine these collocation points. So the important points that I actually care about at determining my phenomenological fit at the end of the day. And let's say, okay, in this case, I have 3 coefficients here, which means I'm going to have 3 collocation points. So it's a symmetric problem here. Then I need to choose an ansatz, right? That depends on the physical parameters, whatever they may be in this particular case, and fit that data set, right, at each of my collocation points. So how do I do that? where you have a very nice linear system of equations that you end up with, which by matrix inversion you can solve, right? So we have at each of the collocation points, I know the value for each of my data set variables, right? So I have my hybrids, I evaluate that at the collocation point, I know what the value is. But of course, what I don't know is how this maps then to my phenomenological coefficients. But you have a nice system of equations here that you can solve simultaneously, and that will give you the values for your coefficients, for your Phenom coefficients as a functions of the different parameters that you have. So that's how this works in practice. And here's the sort of example, right? So we have some function here that we call f of x as a function of x. That is like the black thing. And we find 5 collocation points, which kind of really nicely capture the shape. Then I have my data set that I used. And I evaluate that data set at each of those collocation points. So these are the black dots here, because these are things I know, right? This is what I start with. This is my data set that I have. And when I solve the system of equation, right, I get the fit here across the particular parameter that I have chosen, and I can predict what this is going to look like at each of these parameters, and hence I can evaluate my total phenomenological fit. So this is the super simple 1D sort of example here, right? If you do this hierarchically, you do this layer by layer by layer. But that's kind of the idea how the method works. How good is that? So similar to for the NR surrogate, right, here are some comparisons. And so you can see waveforms here and the two. So here's the 2-2 mode of a couple of simulations here. This is one of the high mass ratio simulations that we have. This is a Q18 simulation here. So one of the ones in the extremes of the parameter space non-processing, right? This is just the aligned spin model here. And here on the other hand side is an equal mass, but very high spin. So this is one of the few high spin simulations that are available from the SXS collaboration. And you can see by eye here, NR in the background, model on top, pretty good agreement. But of course, as before, we actually want to compare now against like a large data set. And in particular, right, we want to compare against numerical relativity simulations to see really how well this phenomenological ansatz is capturing the true evolution in the strong field regime. And so if I draw your attention to the orange one here, that's that particular model. And you can see here also the peak is around 10 to the minus 4 in mismatch, right? It's the same measure as before. It's this mismatch measure. And you can see the numerical relativity error, again, here in gray on the side here. And then you can see a comparison to various other aligned spin models that model the dominant harmonic here. And in particular, right, you can see SUB in RV5. So that's the same model that we talked about, kind of I mentioned before, but no precession, no spin. So we really have no precession, sorry. We have an apples to apples comparison here. And that's here the green distribution. So the takeaway message is with the latest generation that the quadrupole mode for aligned spin binaries, the Phenom X model gives you the most accurate one relative to NR. That is not true when you layer things on. Okay, but if you're just interested in the quadrupole mode for aligned spin systems, then Phenom X does the best. Now, this is still not where we want to be overall, right? So there's lots of room of improvement for all these models, but I just kind of wanted to point that out to you because there's a zoo of things out there. Now, how does the story look like when we include higher order modes? So this was just the 2-2 mode and the 2-2 mode. But of course, we have all these other modes that contribute to the radiation field, right? If you have never looked at this, you can see a projection onto the unit sphere here using the basis functions, which are the spin-weighted spherical harmonics, right? And so you can see hot spots and cold spots in the radiation, and they will be correlated with the different directions on the sky. So the different basis functions will contribute depending on where you're looking, right? So for theta equals phi equals 0, we are at the pole here, and you're going to get essentially just the 2-2 mode. Of course, that's not true. But if you look into the plane, which is kind of the blue shaded region here, so my binary sits here, and I've defined my basis such that, you know, it is aligned with this coordinate system, then you'll see that, you know, the 2-2 falls off and the 2-1 becomes more prominent as you go towards the plane. So that's kind of what I was trying to say before without having an illustration. So if we take these modes into account, then the picture changes. Same as before, mismatches, but now we include the higher order modes. And so the green now, which is the SUB and RV5HM model, on average is now going to be the most accurate one compared to the other models. But look at the scale here, right? We are now at the order of a few times 10 to the minus 3 compared to in our simulations. So there is quite a lot of room of improvement, right? It's almost an order of magnitude that we have decreased the accuracy of the models in all of them, despite, you know, all the dramatic improvements that are present. Yep. No, they included the same number of higher modes here. So this is an apples to apples comparison. They go to L equals 5. Yeah, so they select the modes that are actually modeled in the model and have the, what is the word? The joint subset fit. Yep. Okay, we're kind of running out of time, so I'm going to skip over this super quickly. You can do the same also in the time domain. So the motivation originally was frequency domain because it's faster. We can push it down to the milliseconds. I didn't show a timing plot, but indeed Phenom XAS is the fastest model that is on the market. But if you layer on physics, sometimes it becomes very difficult to keep doing things in the frequency domain, especially when you break symmetries and you get content in negative frequencies, for example, that becomes quite difficult to model very accurately. And so in recent years, there has been a push to do the equivalent, but in the time domain. Right, so the logic is the same. You start with a post-Newtonian baseline. Now you take your favorite Taylor T baseline, for example, and again, you continue your ansatz in the in-spiral phase. You do the same kind of for the merger ring down phases. You join them smoothly together. You do hierarchical fitting methods. The formalism, the kind of strategy is exactly the same, but we're doing it in the time domain. Now that is slower. But the accuracy is still okay-ish, not great for this particular generation, but certainly very good when we layer on the physics, in particular when we layer on precession. Things then become a lot cleaner. And we'll skip over that, but there's a whole family tree of phenoms if you are confused with different layers of physics. And so you can stare at that, and there's a list of references, and the slides are going to be uploaded on the Pumple thing later today. So you have hopefully a whole list of references. But I've been talking about the layers of the physics and making things more complicated. And I want to, the last 10 minutes that we have, very briefly talk about something that is still one of the key outstanding challenges. There has been lots of progress in the last 15 years, but it is still something. And when we look back at the accuracies and the models and pushing the models to better and better accuracy, this is one of the sectors where we really need to continue to improve. And so that concerns the effect of spin-induced orbital precession. A priori, there's no reason for us to believe that all black hole binaries out there should have spins that are perfectly parallel or anti-parallel to the orbital angular momentum of the plane, right? Seems like a very fine-tuned initial condition when you create your binary. Now, there might be some arguments for alignments, but it does not necessarily have to be the case, right? So we really need to model the full 7-dimensional problem, which means arbitrary spin orientations. And when I talk about spin orientation, they are always relative to the orbital angular momentum, the instantaneous orbital angular momentum, which in a Newtonian picture is just orthogonal to the orbital plane, right? R cross V is your standard Newtonian picture that you have in your head. Now, if you allow for this misalignment now, so you have this general case, then the equations of motion become a lot more complicated because of the couplings between the spin and the orbital angular momentum. And in particular, if you have misalignment, you get an additional set of evolution equations that tell us that both the spins of your black holes and the orbital angular momentum of the motion are gonna evolve with time. This is not the case in the aligned spin case, right? for L, it's only the magnitude that's changing, right? We're radiating away angular momentum, but we're not changing how it's pointing. It's always perpendicular. And the plane is just a 2D plane. That's it. Same goes for the spins, though the spin magnitudes at leading order are constant. But this is no longer the case when you allow for this misalignment. And you can see here very cleanly that these are driven by cross terms, right? So the components of the spins that are instantaneously perpendicular to L. That's what's going to give you what causes your vectors to precess, right? You can rewrite this in terms of simple equations where we have just some vector omega cross the spin. Now, the impact of that is that your chirps from these nice ones, very smoothly, monotonically increasing, go to that. They look a lot more complicated. And I guess without me saying much, you can imagine that modeling that is a lot more complicated, right? Yep.
Like, is it like maximum spin 0.5?
Just any spin, really. We just call it S, right? In PN, you don't really make an assumption. So it can be any value. It will depend, right, how much you have in the plane. That will change the strength of precession, right?
Also, the magnitude of the spin would matter if you don't have 0.1, like.
Yeah. Absolutely, right? But at the end of the day, what matters is just the component that is perpendicular to L, right? So even if you have an extremal black hole, but it's predominantly aligned, that's not going to be as important as if I have, like, I could have 0.5 in spin, in spin magnitude dimensionless, but entirely in the plane, right? Entirely perpendicular to L. So that's going to give you a lot more precession effects. Yeah, so it really depends, and it also will look very different, right? Those waveforms. This is one example. And there was a question yesterday about the dynamics. So I show you here a PN evolution of the dynamics of the relative separation of the orbit, right? So it looks indeed a lot more complicated to do. So what happens is, as you can see very nicely here, the direction of the angular momentum is the key point that changes, right? We had an L dot equation, which was not just the magnitude because it's shrinking, but it was also changing its direction. And if you think about it again in the Newtonian picture, and we attach essentially the orbital angular momentum to the plane, right? I've got my coordinate system here, and I've got my binary moving initially in this plane. Then I will have my Newtonian orbital angular momentum being perpendicular, right, to that plane here. But if that is now changing with time, and you think about this as instantaneously being attached, right? So if we're tilting this now this way, right, then my entire plane is going to flip. And that's exactly what you see in the motion here. Now, this changes our PN equations and our dynamics. And in particular, right, what we see is this L vector here. So our orbital angular momentum is going to be moving around a particular direction. And the direction it's moving about is the total angular momentum. And you can see this here in the single spin approximation, for example, or for equal masses, just to make it very simple, where then this J would be approximately a constant direction at leading PN order. But this L is going to move around, right? So the initial opening angle will depend on how much your S cross L term was, right? That's what appeared in the equation. That will set the initial scale. And then as we evolve over time, because the magnitude of L is decreasing, we're going to see that this opening angle, this precession cone angle, is going to open up over time. We can formally define this here as the angle between the orbital angular momentum and J, right? And you can write this down. Let's introduce a total spin, which is just S1 plus S2. And then we work out our dot product. And then we see we have here a dependence on obviously the projections of S onto L. That's the parallel component. And the orthogonal ones, right? And it's really the orthogonal ones, as you can see here, that will be driving how large this cone actually is. So how much precession you have in your system. Now, it is very common to introduce a particular source frame where J, this vector that is roughly constant, defines now your z-axis, right? In the non-processing case, we had exactly that frame as well, right? We decided we have some triad where we have our separation vector, right? If these are my black holes, and this was my n hat here, then I had the direction orthogonal to it, which was my lambda, and then I had the z direction, which of course in a non-processing system is just ln. Now we generalize this here to a system where now my z-axis is defined by j, because that's now roughly constant. So I don't have a weirdly time-dependent frame where I decompose any of my vectors. And then we introduce the beta angle, which was your cone. And then we have alpha here, which now tells me as my L is moving around j, right, how much it precesses. So this is what's known as the precession angle. Now, most of the radiation is along the L axis. So if you are an observer over here, and you look at that binary, and it's now processing, you will see the modulations that come from the fact that your L is now not just pointing in some direction forever, but is actually moving on the sky. And every time it crosses your line of sight, you'll get a peak in the radiation, because that's when you get most of it towards you, right? And then it moves away from you, and it goes down. And so this looks very, very complicated and crazy, right? But we can make this simpler, and this is what many people have been working on over the years, by introducing a time-dependent rotation and going back essentially to the picture we have. Instantaneously, let's think we are moving with the binary. We're sitting on the binary. So I can define a source frame where my L always points along the z-axis. Now, this is not what an observer sees, of course, right? Your inertial observer is not going to see that. But you can transform into this non-inertial frame. And that's characterized by 3 angles, right? It's just an SO3 transformation. So we have this cone angle, which tilts me back to my z-axis. I've got a rotation around the z-axis, which is my precession angle as I'm winding up. And there's another degree of freedom, which links these two together in order to keep up with an additional rotation that you have in the SO3 rotation. And that's it. These are 3 Euler angles, very nice geometric interpretation that allows you to transform into this frame. Why is this relevant? Well, modeling these waveforms when they are like all crazy processing is very, very hard. And I've said many times we want to make the problem easier. So we want to go from something that has a lot of wiggles, and here a nice point also for Barak shows you that you no longer obey the classical hierarchy of higher order modes. Your 2-1 mode in this particular case is no longer a subdominant mode. It actually becomes a dominant mode here as I go to merger. So you really want to have that accurately modeled, right? This is what my poor inertial observer would see. But we are clever about it, and we transform now into this frame where I'm instantaneously aligned with the orbital angular momentum. So I'm kind of faking my aligned spin system, right? And then things look like this. And they look like a lot easier. Most of these crazy wiggles here have disappeared. And I also noticed the hierarchy. The 2-2 mode in black here is still the dominant one, as we have been kind of used to for the past N weeks. And if you want to, you can then kind of squint with your eyes and say, this looks very much like an aligned spin system. So it almost looks like I've kind of deconvolved the precession and the radiation reaction, which gives me the in-spiral of the problem. And you can take it a step further and say, well, let's do the inverse. If I take something that looks aligned spin and I convolve it with some model of the precession dynamics, then I should get something precessing back. Why not, right? If I can do it one way, I can do it the other way. And here's an example from post-Newtonian theory to demonstrate that, where you can see we take the blue one, we twist it up with the exact solutions of the PN precession equations, and we get the red one. And if we have the black one, that's what you get when you just evolve your PN system of equations fully, without any approximations. Takes a lot longer though, of course. And so this is the framework that is used in all models to factor in precession. The surrogate does it, Phenom models do it, EOB does it. One way or the other, we do not directly model the processing modes, but we do a transformation to a co-processing frame, which makes the functions a lot simpler. And then at the end, we've broken this problem down into 2 simpler pieces, and we can wolf them back together to get the full thing. So that's kind of where it is. And there are different approaches to how different models do that in a different way. And this is not what I wanted. But I know I'm over, and I just wanted to show you the final plot, and then we can all go for coffee. Was that they all do this in a different way. The idea is the same, but you can do that in a very different way. For the Phenom models, we do specific approximations. There are specific approximations that EOB uses, and so on and so forth. And what this comes down to is essentially what we have at the moment, and now you have the true comparison for these various flavors of models that we have today that include precession and eccentricity, and are used, and all of you can use. They are publicly available and accessible to you. And you can see the comparison here against the NR surrogate model, which is still considered, of course, the gold standard here. And you can see that, you know, on average, they kind of a few times 10 to the -3 in accuracy relative to the surrogate. And then, of course, the surrogate itself had an error relative to NR simulations. So this is kind of where we are at the moment. And to come back to what Bragg was saying, this is scary because I can relate this mismatch to a distinguishability signal-to-noise ratio. So at some point, if your signal is loud enough, then these small discrepancies will translate into effectively parameter biases. And for today, the SNRs we observe today, a few tens maybe, this is mostly okay, but we are starting to see discrepancies between the different models. And this will most certainly be nowhere near good enough for the next generation. And even if it's 10 years away, that's not a hell of a lot of time to continue working on this problem and really pushing our waveform models by several orders of magnitude to high accuracy. And so I do hope that a lot of you are going to be inspired and will continue to work in this. And I do apologize for running over. So I'm truly done now. Thank you very much.